In this lesson, we're looking at something called inductive reasoning, and the other keyword is conjecture. And with inductive reasoning, the basic idea is we look at several specific examples or situations and make a guess about what would happen next. So a conjecture is basically an educated guess based on examples that we've already seen. Okay, for example, we would use inductive reasoning in this situation where we're building a triangle. Each triangle is building another row on the bottom of the previous one, and then we're counting how many dots are in each picture. If we first observe what's happening, we might notice that from the first to second one we add 2 dots. From the next one we add 3 dots. On the next one we notice that we're adding 4 dots. The next one, 5 dots. If we were asked to give a conjecture without having to draw the total number of dots for the next figure, we could notice the pattern that we have +2, +3, +5, +6. We then see the pattern and say the next one must be +6, giving us the number of 15 plus 6, which gives us 21. So we make a conjecture, a guess, that the next number is 21 based on inductive reasoning, where we look at and find the pattern. We notice in the next pattern that we're first subtracting 4, then we're subtracting 5, then we're subtracting 6, then we're subtracting 7, then we're subtracting 8. And so we make a conjecture or a guess that the next number would be subtracting 9, which would be a negative 19. We often use conjectures in geometric figures, and one of the key is to first look at what we're asked to do. And so we should start by looking at the information and drawing a picture that fits what they're giving us. So we're told to have a segment, so we put A, B, and C on a segment. Now we might ask to be given a conjecture about this, and so I might say, for example, that B is between A and C. Now that doesn't necessarily mean the statement is true or false, it's just a guess based on the picture that I have. Now sometimes we make a conjecture that isn't true. To show that it isn't true, we just need to have one example where it doesn't work. Again, one example where it doesn't work will prove a conjecture false. So sometimes it's a lot easier to prove something false than it is to prove that it's true. To prove that it's true, I have to show that it works for every possibility, which might take a really long time. But for proving false, we just need one example. That's called a counterexample. So if you're asked to find a counterexample, read the problem carefully. Points A, B, and C lie on a line segment, and see if your picture actually reflects exactly what they're saying. For example, we conjectured that B is between A and C. Now, based on our picture, that's true. But is that the only way that we can draw the picture? Actually, it's not, because this statement here did not tell us about the order of the statements. In this picture, A, B, and C still lie on the same line segment, but now C is between A and B, and that one example is enough to show that our conjecture is false. Here's another one. We're given that we have two segments, ST and TU, and that's all we have. We don't want to prove anything more, and we want to prove that T is the midpoint of SU. Maybe this was our conjecture that someone made. Now when we look at this statement right here, it's easy to assume that they're talking about a certain segment. But we need to be careful. Is this the only way that I can draw it? Did they tell me that this only lies on a single statement? I can redraw this picture, putting the point T off of the segment connecting them, meaning that my midpoint would have to be on the segment SU, but T is not on that segment. Since we have one example, we can show that that is false. So to be proven, we need a conjecture that is always true. Now here's one more example from our book. Here we want to find a counterexample for this conjecture. So as we read this, we want to identify exactly what the conjecture is and what exactly the given information was. We have this in two parts. If a flower is red. This is like the part that they gave to us, and they said, looking at this information, what do we know? So as we look at the part, it is a rose, this is our conjecture. That means this information over here is something that we need to have. So we need to have this first in order to show that this always must come as a result. So as we examine this, we might think of this picture. Well, here's a rose that's not red, but we read it carefully, that's not what we need to have. We need to have a red flower, not a rose. So even though we have a white rose, this doesn't address the problem. This is not a counterexample. In the next one, I have some things that are red. Now sure, that helps with this part of it, but it doesn't completely fill what we need to have. And so this one also fails as a counterexample because it is not a flower. In our next one, I've taken a tulip. Now a tulip is a flower, it is red, so we have everything that we need to have, but it is not a rose, proving our conjecture to be false. This is a counterexample because it shows our conjecture is false.